So SN1 and SN2. In chapter 6, we learned how to name alkyl halides, and we've seen the type of alkyl halides in addition to the two main reactions that these alkyl halides usually undergo. One of them is the nucleophilic substitution, that's covered in chapter 6, and the second one would be elimination, that would be covered in chapter 7. Now, in the nucleophilic substitution reactions of alkyl halides, there are always two types, type 1 and type 2. We call them SN1 and SN2. We learned last time some of the differences between the two. So let's review again what are the main differences between them. So the main difference basically is looking at the mechanism will tell us a lot of details. So SN2, it's a mechanism in which you will have a one-step reaction, concerted mechanism, meaning the nucleophile will attack the electrophile, and the electrophile is going to have a leaving group that's going to leave at the same time. So the nucleophilic attack plus the leaving group breaking off happens all at the same time. And that's why you see a transition state. You don't see an intermediate. What's the difference between a transition state and an intermediate? Transition state is when you have a structure that you speculate what it looks like. But an intermediate, it's a structure that you isolate. You are sure of what it is because you do have spectroscopic analysis of it. So that's the difference between a transition state and an intermediate. So it's very important to keep that in mind. So when I look at this energy diagram, I could see clearly that I have a transition state. I don't have an intermediate. What would an intermediate look like? On an energy diagram, it will look like this. So having basically a transition state leading to an intermediate, which will have another transition state lead to the product. So keep that in mind. Every single time you have an SN2 reaction, it's a transition state containing mechanism, and it will always involve the two reactants that are alkyl halide and the nucleophile in the reaction rate. So that's why it's a second order overall, and that's why the rate expression will be written as rate constant times concentration of alkyl halide times concentration of nucleophile. And you could also see another important thing of the mechanism, that is the inversion of configuration. Inversion of configuration. So you can see here the nucleophile comes from the back side of the halide, the back side. So that's why the product is going to have the nucleophile sitting on the opposite side of where the leaving group was sitting. And that's why you see here the product is actually a result of this backside nucleophilic attack. While in the SN1 mechanism, which is not a concerted mechanism, there is always several steps, minimum of two. The first step is the slow rate determining step, which is the formation of the carbocation. And once you have that alkyl halide, kicks off the halide, will form the carbocation. And the carbocation may go rearrangement, and that's why we say there are possible more than two steps. The rearrangement of the carbocation will happen just because of the more substituted carbon that could exist on the adjacent carbon to the carbocation. And having that more stable carbocation will minimize the activation energy needed to go to the next step. That's why the rearrangement will be favored if that structure allows for it. Rearrangement happens in following two possibilities: 1,2 hydride shift or 1,2 methanide shift. Is it a choice? No. It's usually the easier to be done will be the possible route, the more favored route. That will be the 1,2 hydride shift. If there is no hydrogen to shift, then there will be a carbon shift, and we'll see example of that. This mechanism, once you have the carbocation, the third step, if there is rearrangement, third step will be the nucleophilic attack on the carbocation to give you the final product of the SN1 reaction. It's a unimolecular due to the fact that there is only the alkyl halide that the reaction rate determined is based on, and this concentration of the nucleophile will always be based on how substituted the carbon is in the alkyl halide. And we will see that in the ranking of the alkyl halides that are going to undergo SN1 versus SN2. It's a first order reaction. And you can see here the reaction rate is written as basically reaction rate constant times concentration of the alkyl halide. Racemization, stereochemistry of this reaction, because of the formation of the carbocation, which is an sp2 carbon. This carbocation, that's an sp2 carbon, now it's trigonal planar. So it allows the nucleophile to attack from the top or the bottom. And that's why you're always going to form two different structures. One comes from the inversion of configuration, and one comes from the retention of configuration. What is that supposed to mean? It means you will end up basically making a structure that's going to have the nucleophile attacks on the same side where the leaving group was sitting, or attacks from the opposite side, just like the SN2. That's why you end up having two structures. Now be careful, don't label them enantiomers, because what if you end up with a structure that doesn't have that chiral center? Yes, you do have the new group coming in top and bottom, but if the structure is achiral, then I cannot call these two outcome, the inversion of configuration and the retention of configuration, to be a racemic mixture, because they are not enantiomers. So the mechanism was a main difference. Another difference is the type of alkyl halides. And I mentioned previously that the moment you are given a chemical reaction and you are asked to determine, is it going to go through SN1 or is it going to go SN2, the very first factor you need to look at is the alkyl halide type. Methyl X and primary alkyl halides usually go for an SN2 reaction, versus the tertiary alkyl halides will always favor SN1 reactions. And that's definite. So every single time you have a tertiary alkyl halide, don't even think about doing an SN2 reaction. The tertiary alkyl halide will undergo carbocation formation, possible rearrangement, if any, then nucleophilic attack. So it's a first order reaction. If it's a primary alkyl halide or a methyl X, don't go through an SN1 mechanism, because these structures, they are so unstable as carbocations, therefore they don't want to go through that route. So they will always be attacked by the nucleophile in a concerted mechanism pathway to give you the inversion of configuration structure. That's important to keep in mind. And just to remind you that the ranking when it comes to SN1, tertiary, then secondary, then primary, or methyl X, even though primary and methyl X, they don't actually go through an SN1. But let's say they exist, hypothetically, they will be lower in terms of relative rate. The SN1 reaction rate depends on the stability of the carbocation. As I mentioned, the first step in the SN1 is the formation of the carbocation. So you know now that because of that slow rate, or slow step, or the rate determining step, the more substituted the carbon, the more stable it is as a carbocation. Therefore, it will be a faster reaction if it's a more substituted carbon than another. And that's why you see the ranking here goes from tertiary to secondary to primary to a methyl X. I'm going to add to this. If I have a benzylic carbon, if I have an allylic carbon, where would they fall in here? Well, because of the stability of the benzylic carbocation, more than it is for the allylic, more than it is for the tertiary, this ranking will actually be written as the following, to include benzylic carbon and allylic carbons. Benzylic carbon will be number 1, allylic will be number 2, tertiary will be number 3, secondary will be number 4. Primary and methyl X, they rarely go through SN1. Now, the stability of the carbocation of the benzylic and the allylic is due to the resonance stabilization. Go back to chapter 4 and review that part that justifies the stability of the benzylic carbocation and the allylic carbocation. Now, just to remind you of the stability of the substituted carbons, tertiary, secondary, and primary, we use the two factors. One is the the inductive effect, and the other one is the hyperconjugation. So make sure that you are aware of that. These two factors are used to justify the stability of tertiary, secondary versus primary. But if I want to justify the benzylic carbocation stability or allylic carbocation stability over the other ones, then I'm going to have to use the resonance stabilization factor. This is an example of rearrangement. When does rearrangement take place? Only when there is an SN1 mechanism. And I left out that the other type of alkyl halides, that's the secondary alkyl halide that may undergo SN1 or SN2. That's why I would need to consider another factor. And let me go back to it in a minute. Now, this rearrangement phenomena happens when you have a more substituted carbon adjacent to a carbocation. So in this case, I have an alkyl halide that's going to basically form a secondary carbocation, and that secondary carbocation has a tertiary carbon adjacent to it. So that tertiary carbon, what's going to do, it's going to give its hydrogen to that carbon, and that's what we call 1,2 hydride shift, 1,2 hydride shift, and that carbon now, as a result, will carry the plus, and that's the plus that's going to be attacked by the nucleophile. So that's basically the major product in these reactions when there is a rearrangement possibility. Now, if there is no hydride shift to shift, then there will be a methanide or a methyl to be shifted to that carbon. And we're going to see that in the other PowerPoint slides. So that's another major factor between the SN1 versus SN2 mechanism, which is the rearrangement of the carbocation. And as I mentioned, if I have primary alkyl halide or a methyl X, I will go through SN2. If I have a tertiary alkyl halide, I will go through SN1. What if I have a secondary alkyl halide that always has a possibility of both? I will need to look at the next factor, that is the nucleophile being used in those reactions. The strength of the nucleophile plays a role when you have a secondary alkyl halide. There are three categories of nucleophiles: the strong nucleophiles, the moderate, and the weak. It's important that we be aware of these nucleophiles, because I may be asked a question. Label a following reaction with an SN1 or SN2, and it happens to have a secondary alkyl halide. Then I'm going to need to consider the nucleophile. Is it a strong, is it moderate, or is it weak? All right. Well, what if it's a strong nucleophile? Then that secondary alkyl halide will undergo SN2 reaction. Because of the strength of the nucleophile, it's going to be so fast to attack, therefore it will undergo SN2. What if it's a weak nucleophile, one of those three, or even the acid? I mean, I could have a carboxylic acid, I could have an alcohol, water, or fluoride. These are examples of weak nucleophiles. What happens if I see them with a secondary alkyl halide? It will undergo SN1 mechanism, because the carbocation is going to be formed faster than having the nucleophile attacking that Rx. And that's why the reaction will undergo SN1. What if I have a moderate nucleophile, such as Br- or Cl- or the ammonia or the carboxylate or the sulfide? What will happen? Then there's supposed to be a look at the third factor, that is the solvent. And we're gonna look at those solvents to determine whether that moderate nucleophile and the secondary alkyl halide will undergo SN1 versus SN2. So I hope it's very clear now to you that there are three major factors that we always have to consider when it comes to labeling a reaction, SN1 versus SN2. And I cannot just randomly pick one of those factors. It has to be in the order of alkyl halide, then nucleophile, then solvent. And in terms of the trends in nucleophilicity, it's very important that we keep in mind that always the more negatively charged atom will be stronger nucleophile than the corresponding neutral one. The bigger atomic size one will always be more nucleophilic than the smaller atomic size one. So it's very important that we keep always that in mind. Keep in mind that this also affects the SN2 more than it is the SN1. SN1 chemical reaction rate does not get affected by the nucleophilic strength. So that's why if I want to push a reaction to go SN1, I would rather use a weak nucleophile. So it will allow the carbocation to form easily. And that's basically the preference when it comes to an SN1 reaction. And that's the third factor that becomes important when I have the scenario of secondary alkyl halide and moderate nucleophile. If I have a secondary alkyl halide and moderate nucleophile, the reaction can undergo SN1 or SN2. That's why the solvent becomes important as a factor. Only then. What is that supposed to mean? If I have a tertiary alkyl halide and a nucleophile, it doesn't matter what solvent I use, because the tertiary alkyl halide already determined what pathway the reaction should undergo, which is SN1. If I have a primary X or a methyl X, it will undergo SN2, regardless what solvent I use. If I have a secondary alkyl halide with a strong nucleophile, it doesn't matter what solvent to use. It will undergo SN2. If I have a secondary alkyl halide with weak nucleophile, it will undergo SN1, regardless what solvent I use. The solvent becomes like a factor to affect the rate rather than the type of that nucleophilic substitution reaction. And there is a difference here. Am I going with a faster SN2 or am I going with a slower SN2? That's different than saying, oh, is it going to go SN2 or is it going to go SN1? It's totally two different comparisons. So when it comes to solvents being used in nucleophilic substitutions, they always have to be a polar type solvent. And the polar type solvents, there are two types. There is the A product and there is the product. From the definition, what it means that when you have a product solvent, it has an acidic hydrogen. What are examples of product solvents? Alcohols, water, or carboxylic acids. So these are examples of product solvents. What are examples of A product solvents? Structures that do have hydrogens, but they are not acidic. And be careful, when you say A product solvent, it doesn't mean that solvent doesn't have hydrogen. It does have, but they are not acidic hydrogens enough to interfere with the mechanism. What are examples of A product solvents that are polar? Acetone, DMF, dimethyl formamide, acetonitrile. And there is some more we're going to see also in those examples and reactions that we're going to be studying. And those A product solvents, they are usually used in the SN2 reactions. And we're going to see why that is. The polar product solvents, they are favored for the SN1 reaction. And we'll also see a justification for that. So now you are hopefully adding up to that third approach, using the solvent to determine a pathway of a reaction. And when is that reaction, or what is the condition of that reaction that you're going to need to look at the solvent? Secondary alkyl halide, moderate nucleophile. If I have secondary alkyl halide and moderate nucleophile in presence of a polar A product solvent, the reaction will undergo SN2. If I have secondary alkyl halide with moderate nucleophile in presence of a product solvent, the reaction will undergo SN1. Other than that, it's just a matter of chemical reaction rate, faster or slower. What is that supposed to mean? If I have a tertiary alkyl halide reacting with a nucleophile, and I use polar A product solvent, like acetone, for example, I would expect the reaction rate to be slower compared to the same exact alkyl halide, same exact nucleophile done in a polar product solvent. That's how we're going to be looking at it. The same applies if I would be running an SN2 reaction. If I have a primary alkyl X and reacting with a nucleophile to undergo SN2, if I have the solvent methanol instead of acetone, the methanol one was going to have a slower reaction rate compared to the acetone medium one. So that's how we're going to be looking at it. So the solvent as a factor will not determine pathway of a reaction, whether it's SN1 or SN2, unless I have a secondary alkyl halide and a moderate nucleophile. Keep that in mind. Why polar A product is important for SN2 and polar product are important for SN1. So let's look at the polar product solvent. So here is an example. So you can see clearly that you have alcohols, and these alcohols, the way how they affect the SN1 reaction, they tend to basically rip off the CX bond So the H of the product solvent is going to basically chelate to the negative to the halide, and that halide basically is going to be trapped with the acidic hydrogens. And you can see here also the alkyl X, when you have product solvents, that oxygen is going to stabilize the carbocation. So the carbocation of that CX will be pushed to be formed due to the presence of the ROH, so or any product solvent. So the hydrogen will basically interfere with the X, and the oxygen will interfere with the carbon side of that CX, and that will help breaking up the bond of CX to generate the carbocation. So every single time I have an SN1 reaction, I prefer to use polar product solvents, so that way I easily can ionize the CX bond to push the formation of the carbocation plus X minus. And that's the importance of the presence of the polar product solvents in SN1 reactions. And we call that solvolysis. Whether we look at SN1 or SN2 solvent effect, it's called solvolysis. Solvolysis effect becomes important when we push a reaction toward one path over the other, or a reaction rate to be faster than another. So how about the polar A product solvents? Why they are important for an SN2 reaction? These structures don't have an acidic hydrogens, but what do they do? What do they have? They have a polar side in the molecule, like in the acetonitrile, there is a nitrogen with a lone pair. In the DMF, there is the oxygen on the carbonyl, and then the acetone is the oxygen on the carbonyl as well. What do? They do something just like this structure right here. These structures are called crown ethers. They behave just like the polar A product solvents. What they do is the following. I have a nucleophile, and I have an alkyl halide. Alkyl halide to be primary, or methyl X running through an SN2 reaction. The nucleophile is always going to have a counter cation and a counter anion. Like, for example, NaI, KCN, lithium azide, whatever nucleophile has a chemical formula, it's going to always be split into a cation and an anion. The anion will be the nucleophile. The cation is there as a counter cation for the nucleophile, for the negatively charged part. Okay. How would the polar A product solvent help the reaction rate of an SN2? It's gonna do solvolysis, solvating the cationic part of the nucleophile, and once you trap the cationic part of the nucleophile, you're freeing up the nucleophile to attack faster. So for example, if I have KCN, K will be trapped with those molecules of the solvents, whether it's acetone, whether it's DMF, whether it's acetonitrile, or if I have crown ethers, and we're going to come to those in a minute. What they do, those polar parts of these molecules will chelate, form a partial bond. It's not a full bond, but it's chelation, where it basically traps the cationic part of the nucleophile in a cage-like, and that will basically free up the nucleophile to go and attack easily, and that will affect the reaction rate to be faster. And that's what matters in the SN2. Nucleophile and the alkyl halide both are considered when it comes to the reaction rate. So that's why it's important actually that we have a strong nucleophile. Otherwise, the reaction rate will be slower. So in order for us to push the SN2 reaction faster, we have to use strong nucleophiles. What if I have a moderate nucleophile? How can I push this? Well, or a weak nucleophile, how can I push this? Well, here's an example. Look at this. It's a benzyl chloride using KF. What's an F minus? That's a weak nucleophile. This reaction, when it's done without crown ether or polar A product solvent, the reaction gives very low yield. So what's been observed when they use polar A product solvent and crown ethers, they trap the potassium, freeing up the F minus to attack the alkyl halide. And that generated moderate to good yield in those reactions. When we use solvolysis effect as a factor to push the reaction forward. And this is important to keep in mind, that the polar A product solvents are important for SN2, not SN1, due to the fact that they trap the cationic part of the nucleophile to free up the nucleophile to attack the alkyl halide. Crown ethers, similar to that when it comes to justifying their use. Crown ethers are cyclic compounds. There are several types of them. The only difference between them is basically what type of metal cation to be trapped. So the smaller the metal to be trapped, like lithium, for example, I would be using a small crown ether compared to a potassium where it's bigger in size. That's why I will be using a bigger crown ether. What do? They do solvolysis effect, where they basically solvate the cation, so the nucleophilic strength of the anion becomes increased. So that's very important when it comes to nucleophilic substitution. That is an SN2 reaction. I wouldn't be using crown ethers or polar A product solvents if I have an SN1 reaction, because the carbocation is going to be formed easily anyways. So there's no reason to use it. Rather, I would be using polar product solvents. Why? So it could easily rip off the bond between C and X using that acidic hydrogen bonding to the halide part, and the oxygen in the alcohol or the water will basically bond or chelate to the C part of the CX. So that's very important to keep in mind. We could see it here clearly how the ionization happens easily if I use a polar product solvent. You could see here the Rx being ripped apart by having the solvent helping that out, having the oxygen part of the alcohol, for example, being used as a polar product solvent to stabilize the carbocation, and the hydrogen stabilizing the X minus. So that's another type of solvolysis using polar product solvents. So that's very important to keep in mind. So now we understand why SN1 prefers to use polar product solvents, while SN2 prefers to use A product solvents. Another major factor that's a difference between the two type of mechanisms is the stereochemistry. SN2 always generates the inversion of configuration product. SN1, there is a possibility for two structures to be formed. One is the inversion of configuration, and one is the retention of configuration. Inversion of configuration will be slightly higher, but most of the time we say we form a racemic mixture. When we say a racemic mixture, it's equal amounts of the two enantiomers. But the inversion, most of the time, is actually a little higher in terms of yield compared to the retention. So just to remind ourselves how the SN2 mechanism works in terms of stereochemistry, the nucleophile attacks the back loop of the CX, and that basically allows for the overlap of the nucleophile with that orbital of the carbon to basically form a bond. That's a partially formed bond right now, and kick off the CX bond. That's the partially broken bond. And this transition state now, it basically it confirms that I have an inversion of configuration every single time and have an SN2. Because if you have an SN1, you can't just say, oh, I have only an inversion of configuration, because you form the carbocation there. Therefore, there will always two faces allows for the nucleophile to attack. But when it's an SN2, the nucleophile cannot come from the same face of the leaving group. It has to come from the opposite side of the leaving group. That's why it generates the inversion of configuration only. While the SN1, because of the fact that you have an sp2 carbocation, it allows the nucleophile to attack from the top or the bottom, and that's why you end up basically making the retention of configuration outcome plus the inversion of configuration. So you end up making sometime a racemic mixture. And when I say sometime, because some other times where you would see the two structures, that the inversion and the retention are exactly the same. They are both achiral. So you cannot call them racemic mixtures. You cannot call them enantiomers. You still can call them retention of configuration outcome versus inversion of configuration outcome, but be careful to label them enantiomers all the time. You have to look at that chiral center, if it's a really chiral center or not. And here's one. You could see clearly 4 different atoms or groups of atoms, and that's why these two are enantiomers. Another factor, but it affects both at the same time, SN1 and SN2, and that is the leaving group. Do I consider the leaving group as a factor to determine a pathway of a reaction? No, you do not. There are only 3 factors to determine a pathway of a reaction. The alkyl halide type, then the nucleophile if it's a secondary alkyl halide, then the solvent if it's a secondary alkyl halide using moderate nucleophile. So when do we consider the leaving group then as a factor? Only to justify a chemical reaction rate. The better the leaving group, the faster the reaction is, whether we're talking about SN1 or SN2. What's the definition of a better leaving group? The following. The leaving group to be polarized. The more polarizable the bond, or the more polarizable the atom of the leaving group, the better, because that justifies how it's easily ionized to be kicked off. Second, stable as a weak base. So the weaker it is as a base, the more the better it is as a leaving group. And these are the 2 main factors actually: polarizability and basicity. The more polarizable the group, the faster it is, or the better it is as a good leaving group. And the basicity, the weaker it is as a base, the better it is as a leaving group. Here's an example: I minus versus F minus. As a base, I am not given pKb to determine the basicity here, but I already know the conjugate acids. HI is a stronger acid than HF. And if HI is stronger acid than HF, that means I minus is a weaker base than F minus. So F minus is a stronger base than I minus. And that justifies why I minus as a leaving group, it's 30,000 times more reactive than an alkyl fluoride structure. Look at this, tosylate. Tosylate is basically a leaving group that's basically comes from OH. OH is a very weak leaving group. It's a very bad leaving group actually. Alcohols structures, looking at that OH as an anion, it's an OH minus, it's a strong base. So that's why it's a very bad leaving group. And in order for us to make it a better leaving group, we basically convert it to something else that's called tosylate, para-toluene sulfonic sulfonyl chloride, sulfonyl group. And I will be using one of the structures in the examples later on to show you how this tosylate group look like. So this gives me basically the ranking of these leaving groups. So alcohols, amines, and ethers are very bad leaving groups. So if I have an alcohol reacting with a nucleophile, and I'm asked to predict the outcome of a reaction, what do I write? I write no reaction. Why? Because it's a bad leaving group. It cannot leave. If the fact that it's a strong base as an anion, the OH as an OH minus is a strong base. Therefore, it's a bad leaving group. NH2 as an anion, it's an NH2 minus. It's a bad leaving group because it's a strong base. So every single time you are figuring out that it's an alcohol structure or an amine structure or an ether structure or an alkyl fluoride, you automatically just say the reaction outcome will be no reaction, and that's important. Chloride is 200 times better. Bromide is better than chloride. Iodide is better than bromide, and the best leaving group would be tosylate. So how would a question be asked about this? I could be giving you 2-iodobutane versus 2-chlorobutane, and ask you which of the two is faster in SN1. Well, wait a minute. Both of them are a secondary alkyl halides. So it doesn't have to do with the alkyl halide type. It has to do with the halide group that's attached. The better leaving group 1 will be faster reaction rate than the other structure. That's always the case, whether it's an SN1 or an SN2. If I have a methyl bromide versus methyl chloride, we know both going to go through SN2, but which one is going to be faster? Methyl bromide will be faster than a methyl chloride. So that's important to keep in mind. So this is what I want to talk about in this part. Next, we're going to be looking at some more examples of what we discussed in here, and perhaps we'll elaborate some more on the concepts that we covered in this part.